Okay, hi everyone. Thank you so much for coming. It's lovely to see you all here. I just wanted to do a quick little intro, let you know a little bit more about us, and then I'll hand over for what you're actually here for today. So my name is Emma. I'm the events manager here at KIS, and the reason we offer these workshops is to make sure that we have as many resources available for students in year 12 to just make their lives a little bit easier. If you haven't already, check out our free events that we ran on Sunday. They're all up on our YouTube and free. So go ahead, go for your life with those. And if you are studying methods, that is going to be on tomorrow, another Back to Basics. So make sure you get your tickets for that. Just a quick rundown of what will be happening today. Most of the time we will be going through Felix's presentation. Please have your booklets out, which you should have got an email with. Please direct message me if you haven't got your booklet. Just make sure you have that open so you can kind of see what we're going through. We'll also be doing some polls with multiple choice questions, so please engage, stay active, and make sure you're making the most of this session. And we'll also have question time, so chuck anything in the Q&A or the chat, and we'll make sure to do our best to answer everything. That's all from me. So without further ado, Felix, over to you.
Cool. Thank you so much, Emma. Hey, everyone. Just a quick intro to myself before we get started for today. That is me. Right now, I look really sunburnt. I think I am. I graduated in 2019 with an ATAR of 99.6, always nice to say. I started shooting since 2019, so this would have been my 4th year now, which is kind of hectic. I had a 440 in chem, so I know what I'm talking about. I am about to enter my 3rd and final year of biomedicine at UML, and I'm hoping to do postgraduate medicine afterwards, so the very generic Asian pathway there. Fun fact about me, I am absolutely addicted to cats, but I'm actually deathly allergic. So I will literally go out of my way to pet a cat, knowing that my hand's going to be red afterwards, but it's a good life. So throughout this PowerPoint, I've got a bunch of cats to keep us motivated as we go through today's session. So what are we doing for today? Well, in total, we're going to be going over a 1 hour and 30-minute session of just pure chemistry. We're going to be targeting everything you need to know from year 11 and how it translates into year 12. A lot of the questions we're going to be looking at today is based on the VACO study design, and a lot of past questions you might have a go at today. So the first topic we're going to be doing is stoichiometry, the idea of moles, limiting access, all that type of stuff. We'll spend maybe 25 minutes on that. That's roughly, depending on how fast or how slow we go. The second topic is types of reactions. We're going to be revising our redox reactions, as well as acid-base. Because that's a generally larger topic, we're going to be spending a little bit more time on that. And then we're going to finish things up with a bit of organic chemistry, the idea of functional groups, hydrocarbons, all that type of stuff. And we'll have some break in between types of reactions, so we are not completely glued to our screens. And we are going to finish things off with a bit of Q&A in the last 5 minutes. But if you have any questions whatsoever, or if there's something that you want a bit more explanation of, or you feel like I'm going a bit too fast, let me know, drop it in the Q&A. Happy to accommodate. Cool. So in terms of contents, love it. In terms of the syllabus, this is what we're going to be going for today. So 3 topics in together: stoic, reactions, organic. For stoic, we have moles, mole ratios, limiting excess, sig figs. Reactions, acid-base, volumetric analysis, redox, and organic chemistry, hydrocarbons and functional groups, and naming conventions. We're going to go through all of these in pretty in-depth, everything that you'll ever need to know, and more importantly, when to recognize when a question is asking for a certain formula, because that's something a lot of teachers don't say. They tell you how to do something, but don't tell you when to do it. Because for me, at least, the reason why chemistry is hard, because you don't know how to start a question. So that's what I'll be targeting for today's session: how to start a question, more than just here's the content. Okay, cool. And I have this here just for myself. Cool. And just a quick reminder, we're going to be using this booklet as we go throughout for today's session. Feel free to annotate it as much as possible. There should be like blank spaces to fill in your answers. And yeah, should be good. Okay, let's get started. Topic 1, we have stoichiometry. So number 1, what is a mole? So the definition of a mole is we have 6.02 times 10 to the power 23 entities of a particular atom, molecule, or compound. So literally we can have 1 mole of bananas. It's just a butt ton of bananas. More importantly though, chemists use this as a way to uniformly keep track of how much we have and how much we need. If we bring up the example of pens and pen lids, it's not enough to just say we've got 10 grams of a pen lid and 10 grams of a pen barrel. We need to have an exact number though. We need to say we've got 2 pen lids, 2 pen barrels. In the same way that we need to have 2 atoms of sodium, 2 atoms of chloride, not just 5 grams of each. Cool. So in terms of working out ML, we have 3 formulas that we have looked at in year 11. In year 12, we're going to add 2 more formulas onto that. And that's going to do with gases, but we won't be covering that for today. So to revise our formulas on the page over here, this first formula over here, the mole of a substance, one way to calculate that would be to take the total number of atoms and divide that by Avogadro's number of 6.02 times 10 to the power of 23. So for example, if I had 1 billion atoms of sodium, to work out how many moles I had, I'll do 1 billion divided by 6.02 times 10 to the power 23. Cool. Okay, next formula, we have the mole of a substance. This could also be worked out using mass and molar mass. If we have the mass of substance and as well as the molar mass, we get the molar mass, by the way, through our data booklet. There's going to be a year 12 data booklet, and we're going to be studying that like it's the Bible. We can do mass divided by molar mass, and that's also going to tell us the mole of a particular substance. The final way is going to be based on our liquids. We can find the mole of a liquid based on its concentration, as well as how much volume we have. And just an important note here is the units that we need to keep track of when we consider these equations. For our mass formula, our units are always in grams. And for our volume formula, our unit is always in liters. So a really common mistake is people forget to convert milliliters to liters or gigaliters to liters or kilograms to grams. Make sure we maintain the right units. Otherwise, we get to a completely different answer that's a couple thousand digits off. Cool. So hopefully that is just revision. We're going to be looking at an example question now that hits all of those 3 equations. So what I'm going to do is going to give everyone just maybe 1.5 minutes to have a go at answering this question. And then I will reveal my thought process as well as how I know to use which formula. Cool. So I'll just start a quick timer for 1.5 minutes. The time starts now. Good luck. Cool. 30 more seconds. Three, 2, 1. Cool, and that is time. So that is how much time you would usually be expected to spend on this particular type of question in year 12. So congratulations to everyone that decided copper was the substance that had the most amount of moles of. Let's go through the working out now. So if I underline the information to do with HCl over here, is that we have a volume as well as a concentration. So because of this, this tells me that HCl is a liquid or aqueous substance. So I'm going to use the formula mole is equal to concentration times volume. So that's going to be 0.95 times 0.200, not 200 there, with the idea of we need to convert milliliters to liters. So completing that calculation, that takes me to 0.19 moles. If we now have a look at copper, we know the mass of copper. So thinking back to our formulas, we know that the only mole formula related to mass is going to be mole equals mass divided by molar mass. So we're going to do 60 divided by copper's molar mass of 63.5, which is again found in a data booklet. That will take me to 0.94 moles. Finally, we have zinc. This time we are given the number of atoms of zinc. So using the first formula, we know that one way to find moles is going to be number of atoms divided by Avogadro's number. So if we do 1.51 times 10 to the power of 23, all divided by 6.02 times 10 to the power of 23, we should get the answer of 0.25 moles. Cool. So just based on these three numbers, we see that we have the most amount of copper, and therefore copper is what the chemist has most of. Cool. Okay, let's move on to the next topic of mole ratio. So we know how to find the mole of something. Let's think about some of the reasons why we are aiming to find the mole. Cool. So mole ratio is used to predict how much of another substance is needed. And so what I mean by that is if we have some special equation in terms of maybe cars and tires, we know that if we have 10 cars and 10 tires, or 10 car frames and 10 tires, it doesn't mean that we're going to produce 10 cars. In reality, we're only going to produce 2 cars because we don't have enough tires. And so to be able to predict that in a chemical setting, we have the idea of mole ratios. The way that we actually calculate mole ratios is going to be this formula over here. The mole of one thing divided by its coefficient is equal to the mole of another substance divided by its coefficient. And so if I create a random equation real quick to demonstrate this idea, let's look at copper solid combined with 2 Ag aqueous. That will turn into copper 2 plus aqueous as well as 2 Ag solid. And so let's say that we started off with 10 moles of copper. And the question was, how many moles of Ag aqueous do we need to make sure that everything balances out perfectly? The way that I would approach this is by starting off with this formula. I know that the mole of copper divided by its coefficient of 1, in this case, is equal to the mole of Ag aqueous divided by its coefficient of 2. And so subbing our numbers in, I know that 10 divided by 1 is equal to our mole of Ag plus divided by 2. And therefore, the mole of Ag aqueous must be 20. And so by using this formula, I can predict that if I had 10 moles of copper, I need 20 moles of Ag plus to balance this out perfectly. And this happens for both reactants and products. I could have done the exact same equation to work out how many moles of Ag solid would be produced, or how many moles of copper 2 plus would be produced. Cool. Let's have a go at applying that into an actual question now. So what we have over here is going to be the combustion equation for octane. What happens if we combine a fuel with oxygen? So the equation is already balanced out for us, so no need to spend too long balancing out all the carbons, hydrogens, and oxygens. Part A is asking us, what is the mass of oxygen needed to fully combust 2.43 moles of octane? So your hint is think about mole ratios, and I'll give everyone maybe, let's say, another 1.5 minutes, because that would be how long we are expected to spend in year 12. I know that we're not up to that standard just yet because we haven't even started year 12, but for the purpose of time, I might limit it to 1.5. So good luck, time starts now. If anyone has any questions, by the way, feel free to chuck it in chat or Q&A, and I will do my best to get around to you. Cool, 30 more seconds. And time. Cool. So the correct answer is going to be 972 grams. So congratulations to anyone that got that. Let's go through the thought process now. So to use mole ratios, we use this when we are trying to relate one substance to another. So it's giving us information about octane and it's asking for us for a different substance. And because of that, that's a clear indicator that I'm going to be using mole ratios here. So to start off, I'm just going to write down the formula. The mole of octane, which is given to us, divided by its coefficient of 2, is going to be equal to the mole of oxygen, which is what we're trying to find, divided by its coefficient of 25. So just a little bit of rearranging here. We can say that the mole of oxygen is going to be equal to 25 times the mole of octane divided by 2. So if we did 25 times 2.43 divided by 2, we should get to the answer of 30.375 moles. Cool. So that is how much moles, or how many moles of oxygen are needed. To turn this into a mass now, we refer to the earlier formula that we used. We know that mole is equal to mass divided by molar mass, and therefore rearranging a little bit, we can say that the mass of oxygen is equal to mole times molar mass. So if we did 30.375 times the molar mass of 32, that takes us to the answer of 972 grams. Cool. Okay, so that is everything to do with mole ratios. Let's look at how this extends even further now with the idea, or sorry, before that, got a part B to this question. If 80 grams of octane is fully combusted, what is the mass of carbon dioxide produced? So for this, once again, the hint is mole ratios. It is giving us one substance. It is asking for the sum analysis of another substance. So that's the hint. Once again, 1.5 minutes on the clock. Time starts now. Good luck. Forty-five more seconds. Cool, and that is time. Okay, cool. So to go through the thought process of that, very similar to part A, is the idea of we have this equation that we're trying to fulfill. We see that we aren't given the mole of octane straight away, so we need to work that out. The way we work that out is using this formula of mass divided by molar mass. So 80 divided by octane's molar mass of 114, and that gets us to 0.702. From there, we can chuck those numbers into our mole ratios equation, and we can use that to predict how many moles of carbon dioxide is going to be produced. So now that we know how many moles of carbon dioxide is being produced, the final step is simply to convert this into a mass. The mass of carbon dioxide is going to be mole times a molar mass. So if we do 5.614 times a molar mass of 44, that will take us to 247.018 grams. Ooh, so that is how much CO2 is produced if we combusted 80 grams of octane completely. Now, don't worry too much about our sig figs just yet. We'll do a section on sig figs after we have completed all our calculations. Okay, cool. So onto how this extends even more, we have the idea of limiting in excess. So the key principle here is that not every reaction will have the perfect amount of reactants. There's always going to be some reactant that we have more of or some that we have less of. For particular, if you ever do a lot of baking or cooking, you'll see like there's always that one pesky ingredient that you just can't seem to get rid of. Like you never buy the perfect amount. It's just like 100 grams of flour that you can't use anything, so you buy more and you have to restock it. And anyway, a tangent on cooking. So how this applies to chemistry here is that some reactants will be excess, some reactants will be limiting. The way that we actually determine which is going to be excess, which is going to be limiting, is the same idea as mole ratios. The only difference though is that we no longer have an equal sign. We've just got a colon there to, I guess, symbolize that it's not necessarily going to be equal. We're just looking to see which one's going to be used up first. And so what we are going to do here is I will go through part A, and then I'll get everyone else to do part B. So question 3, 20 grams of octane is combusted with 6 grams of oxygen. Part A, calculate which is the limiting factor. And before I do part A, I just want to make a quick note here. Even if the wording of the question didn't say anything explicit in terms of limiting or excess, the way that we recognize to do a limiting or excess type equation is if we are able to find the mole of 2 reactants from the get-go. So for example, if it was like we have 20 grams of octane and then some volume, some concentration of another substance, I know to do limiting excess because we can find 2 moles straight away. And chances are one of these moles is going to be used up first. Okay, cool. So we start off by trying to fulfill this equation. We need to find the mole of octane divided by its coefficient of 2, as well as the mole of oxygen divided by its coefficient of 25. So to find the mole of octane, that is once again going to be mass divided by molar mass of 20 divided by 114. That will get us to 0.175. Likewise, if we do mole of oxygen, that is also going to be mass divided by molar mass, so 6 grams divided by 32. That's going to take us to 0.1875. Cool. So right off the bat, we see that we have less moles of octane than we do of oxygen. But this doesn't necessarily mean that octane is going to be the limiting factor just yet. Instead, we need to apply how many octane molecules do we need and how many oxygen molecules do we need to make a reaction happen. So the way we account for that is by dividing by its coefficient. So if we do 0.175 divided by 2, as well as 0.1875 divided by 25, we get to the numbers of 0.0877 and 0.0075. So just by a quick analysis of which number is higher, which number is bigger, we see that 0.0075 is smaller, and therefore oxygen is going to be the limiting factor. And so what that means in layman's terms means that if we were to complete this reaction, we would run out of oxygen first. So if we completed this until we ran out of oxygen, we would see that we still have some bit of octane left. And so we would say octane would be our excess. Octane would be in excess. Octane in excess. Cool, lovely. So same principles, find the mole, chuck it into the formula. Lovely. Okay, part B, so we spiced it up a little bit. For the reactant that is in excess, calculate how much is left over. So for this, I'll give everyone maybe 1.5 minutes again to go have a go at part B. If you're still taking a bit of time to copy down and not working out, have a go at that. But time starts now. Good luck. 10 more seconds. And time. Okay, cool. So the correct answer there is going to be 0.160 moles. So congratulations to anyone that got that. Let's go through the working out now. So the idea here is we're going to be calculating how much of our octane we are going to be using. Because if we know we started with 0.175 moles of octane, we're going to be subtracting how much we used, and that's going to take us to how much is remaining. So let's think about how much we are using. And to do that, we're going to be using mole ratios once again. So we know that we are using 0.1875 moles of oxygen. So to work out how many moles of octane we're going to be using, we're going to be using our mole ratio equation. We know if we do 0.1875 divided by the coefficient of 25, that is going to be equal to the mole of octane divided by its coefficient of 2. So because we know we are using 100% of oxygen, we can use that to predict how much of octane is being used up. And so by working that out, we see that the amount of octane we are using is going to be 0.015 moles. And so if we start off with 0.175 and we use up 0.015, we end up with 0.160 moles. Cool. Okay, so that is going to be the extent of all the stoichiometry-based calculations in chemistry. The final caveat to all of this is going to be the idea of significant figures. We need to make sure that every number we have as an answer is to the amount of decimal places or figures. Now, the simplest way to work out how many significant figures a number has is we start counting as soon as we encounter a non-zero number. So for example, the value of 0.0519. This would have three sig figs because 0, that is not significant, 0, that is not significant. But as soon as we encounter a non-zero number, in this case 5, every number after that becomes significant. And therefore, we have three sig figs. If we go on to the second example, we see that no, 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 yes. As soon as you encounter the number 4, every number after that is significant. The next example, we see that we have already encountered a significant figure, and so every figure after that becomes significant as well. So therefore, 6.001 has 4 sig figs, even though it's got 2 zeros. And last example, no, no, yes. 0 is not significant, 0 is not significant, but as soon as we encounter the 1, everything after that becomes significant. Cool. So the way we figure out what our answer should be in terms of sig figs is we look at the wording of the question. If a question gives us a bunch of numbers, our answer should follow the same number of sig figs as the smallest number of sig figs in the question. So for example, let's say a question gave us one answer with 5 sig figs, 4 sig figs, 3 sig figs. We should present our answer to 3 sig figs as well. It's always going to be the smallest number. So just a quick example of that. A question contains the values of 10 grams, 0.001 molar, and 0.1 mils. How many sig figs should our answer be? Just maybe give everyone 10 seconds to have a quick think about that. And then we'll move on to the final question for this topic. So if anyone said the answer of 1 sig fig, that would be the correct answer. That is because this first number over here has 3 sig figs. We encounter the 1, and therefore every number after the 1 becomes significant. This only has 1 sig fig because it goes 0, 0, 0, and then an important figure. This number has 2 sig figs because as soon as we encounter a non-zero number, we start counting every number after that as significant. Cool. Okay, so we're going to end off this section with a past exam question. And if I could get Emma, please, to quickly chuck up the poll of options A, B, C, and D. I'll give everyone 2 minutes just to have a quick go at submitting what the answer is. Again, this is year 12 content, so don't feel pressured to be like, I need to get this right. It's the start of year 12 and you haven't even started it, so no pressure whatsoever. Just interested to see if everyone's followed along so far, if there's anything hard about it, anything easy, or just where everyone's at. Cool, so 2 minutes starts now. Good luck. 40 more seconds. If you're not too sure of an answer, feel free to just guess based on a rough estimate of your calculations. Time. Okay, cool.
Okay, we've only had a couple people participate in the poll so far, so I'll give you another like 10 seconds. Just chuck in an answer what you think it might be. Okay, 5, 4, 3, 2, 1. Most people are saying B.
Oh, nice. That is indeed the correct answer. Right. So to go through my thought process here, once again, it's going to be a mole ratio question. The way I know that is because it's giving us information about one substance and it's asking for a completely different substance. So I know to use this formula over here. The mole of ethanol divided by its coefficient of 2 is going to be equal to the mole of carbon dioxide divided by its coefficient of 2. So to fill in this information, the mole of carbon dioxide, that's going to be mass divided by molar mass of 44. That takes us to the number of 0.129. So by filling out this equation, we can say that the mole of ethanol is also equal to 0.139 or C5OH. That's a scuffed 5. And so the final step of working out the mass of ethanol, we do mole times the molar mass, so timesing it by 46. We get to the answer of 5.94 grams, which is the right answer for this particular question. Cool. So yeah, year 12 question, done and dusted. Nice. Okay, so that is all of stoichiometry of year 11. So that's literally like a topic that most schools spend like 4 weeks on, done in 30-ish minutes, which isn't too shabby. Let's move on now into the types of reactions. So just to introduce everyone, we're going to be looking at 2 types of reactions, acid-base as well as redox. And after acid-base, we'll take like a quick 5-minute break. So acid-base reactions, as a reminder, these are going to be reactions involving a transfer of protons or H+ ions, because H+ is just a singular proton, no electrons, no neutrons, just a proton. So we are going to be looking at atoms just chucking H+ at each other and forming new products. Now we have a couple of definitions when it comes to acid-base reactions. For the purpose of year 12, you are never going to see a question that is asking for define an acid or define a base, but it is a good idea to just get a rough idea of what each atom is doing. So acids are going to be giving away H+, bases are going to be accepting H+. When we're talking about a conjugate acid or a base pair, we're going to be talking about 2 substances that differ by 1 proton, for example, hydrochloric acid or Cl-. The strength of an acid or base depends on how readily an acid donates a proton or a base accepts a proton. So for example, if you are a really strong acid, you're going to want to give away your protons like crazy. And if you are a strong base, you want to accept protons extremely readily. So this table over here, this table has been formed by how common acids and bases have appeared throughout VACA papers. So all of these acids and bases, it's not to say that you need to memorize this, but just a rough understanding of, cool, this is going to be a strong acid, which means I'm going to be expecting a lower pH, and this is going to be a stronger base, meaning that I'm going to be expecting a higher pH. So no need to memorize this per se, but it's a good idea just to get a rough basis for, cool, this is an acid, this is the base, this is the pH that I'm expecting. To go through a couple more definitions, because this topic is so definition crazed. We've got monoprotic, diprotic, and polyprotic, which means an acid that can donate 1, 2, or more protons, and it respectively matches up to each slash there over there. We have amphiprotic and amphoteric, the idea that a substance can be both an acceptor and donator of protons. A good example is water. Water can turn into OH minus if it donates a proton, or it can turn into H3O plus if it accepts the proton. Neutralization is going to be the name of the reaction that we're going to be looking at. So a reaction involving an acid and a base. This results in an ionic salt and additional byproducts. Now, I know there's a list out there that says like we have a salt, or we have an acid plus a metal hydroxide, or an acid plus a metal carbonate, and it produces X and Y. I wouldn't recommend memorizing that list. The example that we're going to look at in just a second is going to be testing the idea that there's no memorization needed, just common sense and a bit of interpretation of what we can make with the leftover elements. I'll dive a bit more deeper into that once we look at that particular question. Cool. Another thing that we need to know for acid and base reactions is that questions very commonly ask us about an ionic equation. That is, write the complete ionic equation for the following neutralization. The way we do that is we split our aqueous substances into ions, and then we cancel ions if they appear on both reactant and product side. To go through an example of that real quick before we jump into a proper example, let's have a go at this particular equation. We've got silver nitrate, combining that with sodium chloride, that will produce silver chloride solid plus sodium nitrate aqueous. Cool. So what we have over here is going to be the complete neutralization reaction between sodium chloride and silver nitrate. What we're going to do here is we're going to look at every aqueous substance and split it up into its ions. So for example, silver nitrate, that's going to be split up into Ag plus and NO3 minus. Sodium chloride is going to be split up into Na plus and Cl minus. Now, AgCl, because that is a solid, that does not get split up, but our sodium nitrate, this will indeed get split up. So by looking at all our aqueous substances splitting up, we can now cancel a couple of these out. At least that we've got a Na plus on both sides, so we'll cancel that out. And we've got an NO3 minus on both sides, so we'll cancel that out. And so at the end of the day, the ionic equation is going to look something like this. Turns into AgCl solid. And there we go. So super straightforward way of writing out the ionic equation. We go from the complete equation and then splitting up every single aqueous substance, canceling things out, and just finishing up and simplifying our answer. Cool. Let's have a go at doing that now. So question 5, write both the full and ionic equation for the neutralization of hydrochloric acid with sodium carbonate. So I'll give everyone maybe 2 minutes for this one. And yeah, good luck. One more minute. Cool. And that is time. Okay, cool. So for those that struggled a bit in terms of writing out that acid-base reaction, let's go through my thought process. So I'm going to start off with by saying HCl, hydrochloric acid, combined with sodium carbonate, Na2CO3 aqueous. Cool. So based on what we know about acid-base reactions, no matter what is reacting, we are always going to form a salt. In this case, it's going to be sodium chloride, combining the ionic or anion component of that particular compound with the cation component of the other compound. And so if we have a look at what we have left then, we see that we've got a hydrogen left, we've got a carbon left, and we've got a couple of oxygens left. So based on my chemical understanding, I know that something we can make out of hydrogens, carbons, and oxygen is water and carbon dioxide. And chances are that's what we're going to be producing here. So I'm going to write plus H2O plus carbon dioxide. Cool. Let's have a go at balancing everything out here. Oops, that is going to be aqueous, liquid and gas. We see that we need a number 2 over here and 2 over here to make sure that the sodiums are balanced, because we have 2 sodiums on our left-hand side. And if we require 2 chlorides, we need 2 HCl's on the left-hand side as well. Cool. So just having a quick look at everything else, we see that, yep, sodium's balanced, chloride's balanced, carbon's balanced, oxygen's balanced, hydrogen's balanced, all goes there. So this would be our full equation for the neutralization of hydrochloric acid with sodium carbonate. To go through the thought process of finding the ionic equation now, we're going to be splitting up everything again. So this time it becomes a little bit more complicated because we have our coefficients, but same concept. 2 HCl is going to be 2 H pluses and 2 Cl minuses. Na2 is going to turn into 2 Na plus with a carbon carbonate. We are going to get 2 Na plus with 2 Cl minus. Because water and carbon dioxide are not aqueous, they will stay where they are. Cool. So let's go ahead and cancel some things out. We see that the NAs will cancel out as well as the chlorides, which means the ionic equation will simply be 2H plus combined with carbonate turns into carbon dioxide gas and water liquid. Cool, and there we go. So first line of working out would be our full neutralization reaction. Third line of working out would be our ionic equation there. So yeah, that's what I meant before by the idea of there's no memorization necessarily required in terms of knowing how to write out a neutralization reaction. Just a bit of logical deduction here. If we have hydrogens, carbons, and oxygens left, chances are it's hydrogens or with water and carbon dioxide. Cool, sweet. So let's move on from there now. So now that we know how to write out an acid-base reaction, we need to look at the application component of this now. And the idea of that is going to be called a volumetric analysis, where we're going to be using a known concentration to find an unknown concentration. And here is the particular setup that we would use in a science lab. So just to give maybe a real life example over here, let's say there was we were investigating like a, what should we call it? Baking soda volcano. If we add vinegar and baking soda together, we get an explosion. A very similar concept over here. We're going to be adding 2 substances together to get a color change. Now, based on where that color change occurs, that's going to tell us how much of a substance we had, or how little or how much more of a substance we had for a mystery substance. So a couple of terminology here in terms of all the equipment that is being required to form this experiment. The first one is going to be our burette. So the burette is going to be an extremely accurate measuring device where we alter this tap over here and it drips our titrant into our conical flask. So usually the burette might contain the known solution, and we're going to be slowly dripping more and more of that substance until we get to a color change. The thing that it drips out is going to be called the titrant or the titer. The next component is the pipette. And the pipette is not shown in this diagram, but it is the substance we use. We can just imagine it to be like a, whatchamacallit. If I draw it out real quick, it looks something like this, where if we pinch this thing, that thing up there, it acts as a suction bubble and it's sucked up with a bit of liquid, and we drop it into the conical flask. And once again, it's pretty darn accurate. So we take our pipette and it delivers a set volume into our conical flask. We call this the aliquot. The final component to this is going to be the conical flask itself. It holds the aliquot, and we get the aliquot from our pipette. Now, a good way to remember which instrument we wash with water and which instrument we wash with the expected concentration is that a flask is the only thing we drink out of, like a drinking flask. And therefore, a conical flask is the only thing we are allowed to rinse with water. If we rinse the burette or the pipette with water, it stuffs up our calculations, but it doesn't matter how much we rinse our conical flask, we are still going to get the same answer. For our burette, we should only rinse it with the solution that we're going to be chucking into it, and same thing for our pipette. If, for example, we wanted to store hydrochloric acid and sodium hydroxide in our pipette and burette, that is the substance we rinse our equipment with. So sodium hydroxide, we use that to rinse our pipette because we're going to be using our pipette to pick up sodium hydroxide, and our burette, we're going to be rinsing with hydrochloric acid because it's going to be used to deliver hydrochloric acid. Okay, cool. So that is a massive crash course in volumetric analysis. What I'm going to do over here, a couple more definitions before we look at an example question. Again, these definitions aren't a must for in terms of a year 12 exam, but a lot of schools love to test this on SACs, where it's going to be a 1 marker, define this thing over here. So to go over these definitions real quick, the equivalence point is when reactants are present in the correct ratio. So for example, if we've got 5 moles of sodium hydroxide, 5 moles of hydrochloric acid, we see that that particular mixture has reached its equivalence point. The endpoint is very similar, but it's not an exact measure of equivalence point. We observe the endpoint when there is a visible color change. And so if we mix sodium hydroxide with hydrochloric acid with an indicator, and a color change occurs, we call that the endpoint. Doesn't necessarily mean that it's going to be in the correct ratio, it's just an estimate. What a question means by concordant titers is going to be 3 titers that differ by a maximum of 0.1 mils between the highest and lowest recorded result. So for example, we could have 22.1 mils, we could have 22.15 and 22.17. Cool. So between all of these titers, that is how much of the burette we needed to drop into our conical flask. We see that the maximum difference is less than 0.1, and therefore we would call these 3 titers concordant titers. And then we take the average between these to use for our calculation. So we do 22.1 plus 22.15 plus 22.17 divided by 3, whatever number that was, that's what we use for our calculations. Cool. We have indicators next. That is what we use to indicate a color change based on the pH. So because we know acids and bases have different pHs, we are supposed to use an appropriate indicator to measure that pH change. And in our chemical data booklet, given to us for every second exam, we have a summary for every single indicator we're going to use. So for example, let's say I was combining a really strong acid and base, and just based off the question, we are expecting the pH or the endpoint or equivalence point to be some pH around 8.3 to 10, for example, pH of 9. In that case, it might be good to use a phenolphthalein pH indicator, which will go from colorless to pink. If we use a different indicator, for example, thiamine blue, it might not be able to pick up that color change. It might be yellow for the entire duration, doesn't change color at all. So it's important we pick the right indicator so that we observe when the endpoint is. Okay, cool. Let's now have a look at a past VACA question and see what is expected of us in terms of knowing how a titration experiment is run. So I'm going to give everyone 2 minutes to have a go at question 17 over here. And once again, I'll get Emma to pop up the poll just to get a rough estimate of where everyone's at. And yeah, good luck. Time starts now. I might give 3 minutes actually, just because there's a lot of reading involved. So I'll give 3 minutes altogether. One more minute. Cool, and that is time. Sweet, so quickly finalize entering a guess. Even if you're not too sure, maybe you've narrowed it down to 2 options, just guess from there. Again, not expecting anyone, to be honest, to get this answer because this is year 12 question and we haven't started year 12. But if you did, you are an absolute legend.
Okay, we've got a bit of a split. Oh, we've got a lot of a split. More answers are just coming in. We've got a couple for A, a couple for D, and about 50% for C.
Oh, interesting, interesting. Congratulations then to everyone that said D. D is the right answer once again. So let's go through the working out for that. So what I've done over here is just a quick diagram summarizing these steps. What we're doing is we're going to be dropping our potassium permanganate into our rhubarb extract until we get a complete reaction. And so the idea here is, once again, more ratios. We know one substance, let's use more ratios to work out the mole of a mystery substance. So to find the known concentration, we know 2 pieces of information about our burette or our titrant, titer. That is, we are delivering 21.7 mils with a concentration of 0.02. And so what we can use with this information is find the mole of potassium permanganate. That's going to be 0.0217 times 0.02. And that is going to take us to 0.000434 moles. Cool. So just to pause there, by analyzing our question and just looking at the numbers here, we know that that is how many moles of our potassium permanganate that has been delivered into our conical flask. And so what we can now is use the idea of mole ratio to figure out how many moles of our rhubarb extract did we have in the conical flask to begin with. So I'm going to say the mole of our rhubarb extract of H2C2O4 divided by its coefficient of 5 is equal to the mole of our potassium permanganate divided by its coefficient of 2. Looking at the equation given to us there. So I'm just going to work up to over here now. Based off of this, we can say that the mole of our rhubarb extract has an amount of 0.001085 moles. Cool. So step 1, we have found the mole of the known solution. Step 2, we have used mole ratios to predict how much was in the conical flask. So now that we know the amount of a rhubarb extract that was in the conical flask, to turn this into a concentration now, oops, yeah, C2O4, we need to follow the formula of mole divided by volume. So we know the mole, we know the volume, it's going to be 20 mils, not 200 mils there. The reason, oh, sorry, did I say D was the right answer? I meant to say A. Sorry about that, A is the right answer. Sorry to scare anyone that got D there. A is indeed the right answer. I have completely misread my own handwriting. But to quickly finish this, we can say the mole is 0.001085. Our volume is going to be 0.02. Keeping in mind that we're going to turn milliliters to liters. And the reason why I've chosen to use the 20 mil number as opposed to the 200 mil number is because it doesn't matter what size the conical flask was. It doesn't matter if I place my aliquot into a 1,000 liter conical flask, it doesn't change how much rhubarb there was in the first place. So to find the concentration rhubarb, I'm looking at where we got the rhubarb from, and that was the 20 mil aliquot. So we take that number divided by 0.02, and we get to 0.05425, which matches up with option A there. Cool. So I think the percentage of people that got this question right was maybe like 30 to 40%. Not too certain. Definitely need to double check on that. But definitely a tough question in terms of knowing where to start. But what we see over here is we're able to follow our guiding principles. We are able to find the mole of something. We know to use mole ratios because it's giving us one substance and asking us to find the mole of another substance. And we know to go from a mole into a concentration by dividing it by volume. So 3 steps altogether, but knowing when to do those 3 steps, that's the hard part. Cool. So let's move on from there. We'll do one more question before we take a quick 5-minute break because it's been a 1-hour session. Good question to take a break on. Question 18, which of the following rinses is least likely to affect the accuracy of the results? So think back to what I said before in terms of what happens if we rinse this with that or rinse this instrument with that. Have a go at answering this question. I'll give maybe 30, 45 seconds to have a go. No calculation needed for this one.
Okay, we've got pretty much everyone answered, just waiting on another couple of people.
10 more seconds. Even if you're not too sure, feel free to chuck in a guess if you're limited down to 2 or 3 options. And time.
Okay, so the majority said D, but we also have a few votes for A.
Ah, interesting. Cool. The answer this time is indeed D. Ooh. D. Cool. So the reasoning for that is because a flask is the only thing that can be rinsed with water. So if we rinse our flask with water, that's not going to affect the accuracy of the results. We're looking for least likely here. So that's what we're supposed to do. So hopefully it doesn't affect our results. If we look at all the other options here, a burette is what we are supposed to rinse with what we are filling up with. And B and C are switched the other way around. If we rinsed our burette with our potassium permanganate, that would be good. That would be A-OK. If we rinsed our pipette with our rhubarb extract, that would be A-OK as well. But if we mix and match it, that is bad. That is making reactions occur before we have even done our burette titration. Cool, so that is why D is the right answer. So I'll give everyone now a 5-minute break before we jump into redox reactions as well as organic chemistry. Feel free to just completely leave your screen or maybe take this time to just read off on questions that you've done or look forward into what we're going to do, or feel free to chuck me a question in the chat. Whether that's about like how to do well in year 12, if a topic is going to be tested, how to survive chemistry, any study tips, memory tips, anything like that, happy to spill my knowledge. So cool, I will see everyone in 5 minutes. Otherwise, sit tight.
So Felix, just for me, are you available for tutoring at the moment?
Unfortunately, I am not. I am maxed out my
You're
capacity.
too popular.
Yeah, I do have a wait list. I don't know if like KIS has implemented a wait list though. So
Yeah, I don't think so. But if you do want a tutor similar to Felix from KIS, you can. Oh, sorry, that was not meant for everyone else. I don't know how to delete that. Please ignore that. That's from something complete. That's a uni related thing. I meant to paste a link. Ignore that. So if you would like a tutor from KIS, we have a program called Find a Tutor. And you can kind of like search our little database, look at everyone's bios and work out what you want from there. So check that out if you want. Yeah, okay, that's super awkward. Also, if you have been enjoying this event, or even if you haven't, we would like to get some feedback so we can improve in the future. So I will just grab a link for our feedback form, and you can check that out. Also, for everyone who came in a little bit late and missed my initial spiel, we've got some free resources up on our YouTube, which you can watch. As I said, they're free, so go ahead and check those out. This is the link for that. So many links. This is why I got confused. So yeah, check those out. Super helpful about English and about just surviving year 12 in general. And yeah, I think we've got a couple questions coming through to me, so I'll read them out for you, Felix. The first one is, how did you balance study and other things during year 12?
cool, great question. So for me, just before I say any advice, I just want to say, take everything I say with a grain of salt here. This is what worked for me, and I don't want to apply my sample size of 1 into every person I meet so that it's supposed to work for them. This is just what worked for me. So when I was in year 12, I had a bunch of commitments in terms like sport, violin, leadership, studies. So in terms of balancing things out, if there's one thing that I would recommend is being able to schedule your day appropriately. That is, you know when you have certain periods of free time, as well as when you're going to be really hectic. So a really important skill to have in year 12 is being able to predict how long you're going to need to study something as opposed to how long you have. So for example, if I'm going to like a violin competition, I know that I've got a bit of time on the bus trip to there or the car trip back. Or if I'm going to school, I get driven to school and I take the bus home from high school. So I know that I've got a bit of time to study there. Of course, as well as like lunch times, recesses, free periods, it would be if there's an upcoming SAC, I would block that out to just study. If there wasn't, I would just go ahead, eat lunch, socialize, play a bit of soccer, the traditional jazz there. Yeah, so being able to predict when you're free and when you're not free, I think that's a really good skill to have. And it makes it so that you are not wasting your time. Because something I found in year 12 was that for the first term, I found that I had like a bunch of free periods, but I was feeling really busy. Like I had so much to do on my to-do list But in the blocks that I was free, I wasn't expecting myself to be free. And so I didn't know what I had to do. So if you're able to plan ahead, that would be very much appreciated. Yeah. Cool. Any other questions, Emma?
Not that I can see at the moment. I know we have a question time later, so I don't want to like overwhelm people with that. I think we should probably just head back into it since we only have about 20 minutes left.
Cool. Sounds good. Okay, sweet. So to go over redox reactions are going to be instead a transfer of protons, now it's going to be a transfer of electrons, E minus here. In terms of redox, there's going to be 3 fundamental skills that carry over from year 11 into year 12. The first one is to assign our oxidation numbers. These are going to be imaginary numbers that we fill out according to each atom that tells us if they're going to be a reductant or an oxidant. Now, the acronym we have to assign these oxidation numbers was 1,2-FHO. And the idea behind this is if we have a compound, for example, sodium carbonate. Actually, I'll make it a bit hard. I'll do sodium sulfate. If I wanted to assign oxidation numbers here, I would go through my priority list. That is there a group 1 metal? If so, that has an oxidation number of +1. And in this case, sodium is a group 1, and so I'll chuck a +1 there. Second list is there a group 2 metal? In this case, there is not, so I skip that. Third one is there fluoride? No, there is not. Is there hydrogen? No, there is not. Is there an oxygen? There is. Oxygen will go -2. So after I have gone through this list, I'm just going to quickly make sure that everything balances out to 0. We've got a +1 over here. Because I've got 4 oxygens, that takes me to -8. And therefore, to counterbalance everything, I know that my sulfate must have an oxidation number of +7 there. Lovely, cool. So the second important skill is cohes. Whenever we write out a half equation, we need to make sure that we are able to balance out that half equation through the idea of cohes. Now, what cohes stands for is key element, oxygens, hydrogens, electrons, and then states. So our key element, that is going to be any element other than oxygen or hydrogen. So for example, sodium could be a key element. Just depends on whatever half equation we're going to write here. Oxygens. The way we balance out our oxygens is we add H2O to a particular side over there. So let's say on the right-hand side, we had 5 oxygens, and on the left-hand side, we didn't have any. The way that we would balance this out is we add 5 oxygens or 5 waters to the side that doesn't have any oxygens. Cool. Onto our hydrogens, the way we balance out our hydrogens is we add H+ to a side that is missing any hydrogens. So once again, if we have 10 hydrogens on the left, we go 10 H+ to the right to balance it out. E stands for electrons. The way we balance out electrons is by looking at what side has an excess positive charge. So for example, if we had one side of the equation that had a charge of +7 and the other side had a neutral charge, what I would do is I would add 7 electrons to that side of the positive charge. Because we need to keep in mind here, electrons are negative. So if I want to go from a +7 into a neutral, I need 7 negative electrons to balance it out. And the final S stands for states. That's just making sure we've got gases, liquids, solids, aqueous substances, all labeled out correctly. Cool. The third and final skill that translates into year 12 is going to be writing out a full redox equation. So after we have written out the half equation, we need to be able to predict what is going to be the full reaction that's going to occur. The way we do that is by canceling out our electrons. The idea behind that is our full equation should not have any electrons. So we are going to do times maybe the second plus 3 times the first, such that if we combine our equations together, they cancel out our electrons in the process. Cool. How this extends a little bit into year 12 now is going to be a new acronym called an oil cat rig. I believe in year 11, we would have all looked at the acronym oil rig. To extend on a bit of that, we're going to look at the application component of redox. That is what exactly is occurring when we combine an oxidant and a reductant together. So what this acronym stands for is that oxidation is a loss of electrons, and this will occur at the anode. That is what an oil stands for. Cathode means that reduction, which is a gain of electrons, that is going to occur at the cathode. So what I mean by these two words of anode and cathode is if we refer to a galvanic cell or a diagram that looks something like this. This is how we apply our redox knowledge into an application question. What we have over here is a kind of battery where they've labeled our electrodes for us. We see that over here is our anode, the right cell is our cathode. What we are going to be doing here is able to predict what's going to occur at the anode. We know oxidation is going to occur. So for example, oxidation is a loss of electrons. And so the half equation might look something like this. We see that the zinc is losing electrons that it is dissociating into zinc 2 plus and 2 electrons that are going elsewhere. At the cathode, because a reduction is occurring and reduction is a gain of electrons, this equation might look something like this. We see that copper 2 plus is gaining 2 electrons to turn into copper solid. So key takeaway message here is that if we have electrons on the right-hand side, that means we are losing them. We are starting from our reactant and it's turning into electrons that get sent elsewhere. If we have electrons on the left-hand side, that means our reactants are gaining electrons. We're going to be combining with them to form a product. Let's have a look at a Year 12 question now. This is going to be from the 2017 Chem Exam question 6, multiple choice once again. The question is asking us, here is a particular fuel cell with the equation shown below. What is going to be the reaction that occurs at the cathode? And we have 4 options here. So I'll give everyone maybe a minute this time just to go through the thought process, and I'll get Emma to pop up the poll once more to gauge where everyone's at. Well, thank you very much, Emma. Oh, 5 more seconds. And time. Cool. So if you're just finishing up submitting your answers.
People are rapidly submitting when you said time.
Damn, sorry to rush you guys, but we are just trying to make it time here. Yeah.
We have an even split between A, B, and C.
Oh, damn. Okay. Controversial. Okay, let's go through my thought process.
No, C's just pulled ahead. C's just pulled ahead.
Oh, interesting, interesting. The correct answer is indeed C. So good job to everyone that got C there. So to go through my thought process, we're looking for the cathode equation there. So according to our acronym before, an oil cathode, we are looking for a reduction half equation. And what we know about reduction is we have a gain of electrons. So what we are going to be expecting here is something that looks like A and C. Because if we have a look at B and D, they're not going to be gaining electrons, they're losing electrons. They are sending these electrons to somewhere else. So it narrows it down to 50-50. The way that we decide between A and C is looking at what exactly we are going to be reducing. Now, if we have a look at carbon dioxide in here, we see that that's actually in the product side, and therefore it can't be the half equation for carbon dioxide because we don't have any carbon dioxide to start with. We are producing carbon dioxide. So by process of elimination, we know that C is the right answer. We know that we have starting out with oxygen, that we are going to be combining that and adding electrons into that to turn that into OH minus. Cool. Okay, let's move on now to the final topic for today. Hopefully we're gonna smash this out in like 10 minutes. Okay, so organic chemistry. The first thing that we're going to do is just for revise all of our terminology in terms of our prefixes and our suffixes. So in terms of prefixes, we have all of these, and I just want everyone to add in the numbers of 1, 2, 3, all the way up to 10 there. And so if we ever see a hydrocarbon with the prefix of hex, for example, that tells us that that hydrocarbon has 6 carbons. What I mean by hydrocarbon is a molecule that only contains hydrogens and carbons. For our suffixes, we have ane, ene, and ine. What they represent is the double bonds or triple bonds that a substance will have. So for example, a ane molecule, for example, hexane, that is going to be a 6-carbon molecule with only single bonds. If it is hexene, that means we have double bonds occurring. Now that might be 1, 2, or more. We need more information to tell us that. For iron, that is going to be our triple bonds. So for example, hexine, that's going to be a triple bond somewhere within our 6-carbon molecule. A good way to memorize our prefixes is the acronym Mary eats peanut butter, or methane, ethane, propane, butane. And then for the rest, if we think about our Roman or Latin prefixes, not too certain which one's which, we know that, for example, pent is like pentakill or pentagon with 5 sides, hexagons, octagons, decagons, heptagons, nonagons. They follow the traditional naming system. So it's really just the first 4 that a lot of people have trouble with. We have an example question over here that I might just take everyone through for the first time. Question 8, draw the chemical structure of but1ene. So to break this down, the word or prefix of but tells me that we are going to be looking at a 4-carbon molecule. Ene tells me that we have a double bond somewhere in this molecule. And this number 1 over here, that tells me where that double bond is going to be. So that number 1 tells me that the double bond is going to be connected onto the first carbon or based off of the first carbon. And that's the only position. And so to fill out the rest of these carbons, I need to make sure that every carbon has 4 bonds attached to it. And so the molecule of but1ene is going to look something like this. Altogether, 4 carbons, 1 double bond. Every carbon has 4 lines coming out of it because of the idea of 4 valence electrons. And every line coming out of it is going to be connected to either another carbon or a hydrogen. Okay. Cool. Let's quickly move on to our functional groups now. So functional groups, as implied by the name, is given to a molecule that gives it a certain function. We looked at 3 functional groups in year 11, hydroxyl groups or alcohol groups, which is when we have an OH attached to a group. We have our carboxyl groups, which is our C double bond OH, as well as an ester group over there. This is going to be a C double bond OO. What we might do for the purpose of time is I'll just draw a couple of examples of each of these. But instead of going on to our exam question over there, for our carboxyl, this might look something like this. And for our ester, we might have something that looks like this. Oops. H. Cool. So what we see over here is I'm just going to quickly circle all of the functional groups that give something or give a molecule its particular characteristic. That is, a hydroxyl group is going to be an OH attached to a carbon. A carboxyl group is going to be a C double bond O with an OH attached to a carbon. And finally, ester is going to be our Q functional group over there. So I would say that the most important aspects of these functional groups is that it makes our molecule polar. It gives our molecule the opportunity to do hydrogen bonding, and therefore it's going to be possibly dissolved in water. It's going to have a higher melting point because of the idea that hydrogen bonds are really strong. Cool. So the way that this extends into year 12 is that we will still be testing on this. We're going to be covering a few more functional groups with the idea of ketones, aldehydes, amines, all that type of jazz. And so we need some way to keep track of how to name them. So we're just going to quickly skip this exam question over here feel free to have a go at this in your own time. The answers for this exam question can be found up if you search VACA 2017 chemistry exam examiner's report. This is from question 1, option D, or question D. This question can be answered straight away, no need for any additional Year 12 knowledge here. So to extend on to what I was saying before, because we're going to be learning about a bunch more function groups in Year 12, we have a naming convention that we need to follow when it comes to naming all of these functional groups. And they follow something called the IUPAC system, where it follows a low to high priority, where if something is a low priority, we don't really care about it. If something is a high priority, that is what we label as carbon number 1. So the 3-step process that we go through for naming any type of molecule is number 1, identify the longest carbon chain. Number 2, identify the main functional group. And to do that, we refer to this table over here. If it's got an amide, we turn that into amide. So for example, propamide. Or if there was an aldehyde, we would call it propanol. If there was an ester, we'll say propanoate, and so on and so forth. If there are 2 or more functional groups, we would need to refer to this table over here, and it's going to be the one of the highest priority. So for example, let's say there was a ketone as well as an alcohol. We would call this an propanone as opposed to propanol, with the idea that ketones are higher priority. The final step is going to be naming the carbons. Carbon number 1 will be the end of the carbon chain closest to the main functional group. So if we have a massive carbon chain and we've got one side has an ester, the other side has an alcohol, the side of the ester, that would be carbon number 1 because esters take priority. So let's have a go at implementing this into our final question for today. To end of our session, we have this question over here. What is the IUPAC name of the molecule shown below? Once again, this is a past VACA question. Yeah, good luck. There will be a little bit of Year 12 knowledge needed for this question. So again, no pressure to get this right. I might give maybe 40 seconds, just so we end on time and have a bit of time to ask questions. Yeah, good luck. I know that was barely any time, but for the interest of time, could I get everyone to just quickly submit a guess? Doesn't matter if it's right or wrong. Honestly, just want some interactive component for now. Yeah, and we'll wrap up the poll.
Okay, we've got a few people trickling in. Majority is saying A. We've got a few on B as well.
Oh, nice. Well, good stuff. I have completely bamboozled everyone. The answer this time is D. And here's my thought process for that. So step number 1, find the longest carbon chain. That is going to be this carbon chain over here. So we know that our answer should have something along the lines of pentane. And so what that means is that cancels out A and B straight away, because that is going to be ethyl propane and methyl propane. Because everything is connected onto the same carbon branch, it's actually just going to be pentane. I know it's like really funky looking, seeing how it's like a zigzag shape, but it doesn't matter what the configuration is as long as it's one carbon connected to the next. So then we get left with the options of, is it 3-hydroxy or 1-amino pentanol? And the way we decide which one's which is keeping in mind our priority list. We see that if we have an NH2 group, that is a lower priority than if we had an alcohol group. So if I circle our groups here, this is our NH2 group, and over here is our alcohol group. And so what that means is because we have an alcohol group, our molecule is going to end with the suffix of -ol. And therefore, option D is the right answer there. So yeah, I know that was like just chucking everyone into the deep end there, but this is what is expected into year 12, with the idea of here's some more function groups, here's a couple more rules when it comes to naming things. So yeah, with that being said, that is absolutely everything in year 11 done in 1 hour and 27 minutes. So not too shabby. Hopefully everyone now is fully prepared to enter year 12 with a fresh start and hopefully additional knowledge when it comes to getting ahead of your peers. Yeah, so what we have now is just a bit of time for a couple of questions you want to chuck my way, whether that's content, study techniques, anything VCE or year 12 related. Otherwise, thank you very much for joining me on this amazing journey, and thanks Emma for hosting. Feel free to stay back a bit just to chat, but otherwise, feel free to go.
Awesome. Thanks so much, Felix. I just want to thank you for giving up your time and for passing on what I hope was super helpful to everyone. I did chemistry in year 11 and 12 and haven't touched it since. I'm a law student, so that was a bit of a blast from the past for me to listen in on. We've got a couple questions just coming in now. So the first one is, I think I can just answer this. It's asking if there will be a recording. Yes, there will be. So because this is a paid event, we're obviously not going to put it on our YouTube. We're going to be putting it on our online courses page. So you've got an email from me with the booklet. If you want to reply to that email requesting the recording, I can give you access to it behind the paywall, give you a login and all of that. So yeah, just shoot me an email if you want a recording of that. And besides from that, I don't think we have any other questions open in the Q&A. So I'm happy to wrap up there. I think that was like a really informative session. And yeah, super proud to have the KIS name on it.
Awesome, awesome, awesome. Well, thanks everyone for joining in and shooting in once again. Have a good one. All the best for year 12.
Okay, bye guys.